Hello, Math Studies students. Welcome to another online lesson. Today we're going to be starting a new topic dealing with chi-squared. Chi-squared is a big topic for us. We'll be using this primarily on our projects, which will count as our second semester final, and we'll begin work on those shortly. But chi-squared, and again it's pronounced chi, sort of like if you were to spell the word kite, chi. Or to say hi to someone, hello, hi, put a cuss sound in front. So chi-squared test for independence. It's not chi, it's not chai, it's not any of those other things. Chi-squared. So we're just introducing it. It's a more involved process. We'll be doing it both with technology and without, but today we are going to focus on without technology. So to start off with, we need an actual formula. And our formula for chi-squared is as follows. Chi-squared, chi is a Greek letter, and it looks a lot like an X. When I make it, I just make it with a longer slash and make sure to do italics on the other part. So again, like you're making a regular X, but then do a longer slash there, and that is chi. So chi-squared, meaning that we're going to be squaring something, multiplying it by itself. The chi-squared test is the test that we use to find if two classifications from the same sample are independent. It's a mouthful there. So classifications, what we're talking about is categorical variables. If you have two different categories, two different classifications, and are they independent? If they're independent, what that means is one does not affect the other, like independence that we had back in probability. Let's think of two classifications, like height of person and how well they perform in school. Maybe taller people do well in school. A chi-squared test would allow us to determine if there is a relationship between these, a significant statistical relationship between these, or if they are independent, meaning that the occurrence of one does not affect the other, and I would expect that these would be independent. And the chi-squared test would confirm that. Things that might be more related maybe are things like the number of hours you work and the amount of pay you get or something like that. Those might be categories that are more related. And again, you could test that on a chi-squared test. These are some of the sorts of things that we'll be doing for our project. Anyway, we're going to look at this actual formula that we've got here. It reminds me a little bit of the formula that we had for standard deviation because it's got all these fancy math, little Greek letters and things like that in there. So you've got the chi-squared, that's what we're finding. We're finding a chi-squared value. Then we've got this big old Greek letter here, which looks like a big E, but we know it's sigma, and we know that means sum, add up. What are we adding up? Well, we're taking what's called our observed data minus our expected data, and we're squaring that. Once we square it, we divide it by the expected data, and we do that for every single piece of data and then add them all up. So again, F sub O is observed frequency, F sub E is expected frequency. And I will show you how to get those in just a moment. So before we can do a chi-squared, we first have to turn observed data into expected data. This slide is confusing. There's no two ways about it. If we have some labels, R and R, S and S, basically meaning like maybe these are two different classes that people take right here, and these are different genders of people, and you're trying to find if there's a relationship between genders and the class they take. We've seen tables like this in probability. What makes it weird is that there's no actual words here, it's just letters. So we call this a contingency table or a two-way table. It's a two-way table as opposed to a one-way because you've got two different classifications of things. You got these R's here, which I said could represent gender or something like that, and then you have these which could represent classes or different things like that, different groupings. When we turn the contingency table into an expected value table, we take our observed values, A, B, C, D, etc., and they get manipulated. So let's take a step back. You got an A, you got a B, you got a C, you got a D. It's just a table with numbers in it. So there were a certain number of people that we're calling A that were part of both this group and this group. We have more people B who are part of this group and this group here. And then we can find the total by taking A plus B, and that would equal W. Then I can take the total of these folks here, and that would add up to be X. And then if I add up W and X, I get N. If I add up B and D, I get Z. If I add up A and C, I get Y. And if I do Y plus Z, again, I should end up with N. If you go back to any of your old probability worksheets, you've seen tables like that. So now we've got this stuff. Again, A, B, C, and D were the numbers, the original observed data. Y, Z, W, X, and N are just totals. If you look at our expected value table, take a moment and look. Do you see A, B, C, and D there anywhere? Anywhere on this expected value table? And the answer is no. They're not used. All that's used are a lot of W, Y, N, W, Z, N, W's, N's, X's. These were all the variables that were in the totals in the first place. So now we're looking for a pattern. How do we turn this stuff from the totals, the blue, into what we have here in our expected value table? Well, let's look at the first row with R1. What was the total from that row? It was W. Let's look at our first column, the S1. The total from that one was Y. The grand total was N. And here we are, R1, first row, first column. It takes W and it takes Y, which was the total from this row and the total from this column. They got multiplied together and then divided by the grand total. Now I move on to S2 with R1. Well, again, I take the total from this column right here, which was this Z value. I take the total from this row, which was the W value, and I multiply those together, divided by the grand total. This row, I take the total from that one, which is an X. If I want to do this here, I take the column as well, which was a Y, and notice you see X times Y, again divided by this grand total of N. So every box that we're talking about for expected values, you look at the total from its row, the total from its column, multiply them together, and divide by the grand total. Again, pause this if you need to and see if you can make some sense out of what's going on here. We're going to try now doing a real life, or more so, example. Table shows the results of a sample of 75 randomly selected students, and were classified according to gender and amount of sleep each night. So two different classifications. Do you get a lot of sleep, and what's your gender? They broke it into two categories, male, and for each one, or two choices, two very different values for the variable. You can either have male or female. Oops, sorry, my board's not working here. Male or female. And then you could get at least 8 hours of sleep or get less than that. So we're getting enough sleep or we're not getting enough sleep. We're either male or we're female. Those are our different categories. Now, if we look at this, we can see that there were 12 males who got enough sleep. There were 21 that did not. And then for the females, we have 16 that got enough sleep, 26 that did not. I've already done the sums for you, but we can see where those come from. The blues add up to become the 42 here. The reds add up to become 33 here. Now, if we work down the columns, the 12 and the 16 adds up to 28. The 21 and the 26 adds up to be 47. And if I take these things that are circled in green and add those up, my grand total is 75, which is also the same for this sum column right here. Again, just a table, no different than what we'd seen in probability. Now what we're going to do is we're going to make our expected value table. The expected value table is the exact same size as the original table. It's got the exact same number of values. So we had 4 rows. We're going to have 4 rows in this one as well. We titled this male and female. That stays the same. At least 8 hours of sleep. Less than 8 hours of sleep. Again, I could write it the same way. I'm just paraphrasing here to save time and space. And then we, of course, have our sums, which means total. From the last slide, we saw that none of this quote-unquote observed data got used for our expected value table. The only thing we carried down were the sums. So we're going to have the sums here: 33, 42, 75, and then 28 and 47. Now, in order to get this first value right here, I'm in the male row, and I'm in the greater than 8 hours sleep. Well, the column here has a total of 28. So I'm going to take that 28 that we see at the bottom of the column, and I'm going to multiply it times the total from the row, which is 33, and then divide by the grand total, which we see in the bottom right corner at 75. We can throw that in the calculator. Now, you have to be careful when you put this in the calculator because there is a group, 28 times 33, so we should use parentheses there or do it in multiple steps. But 28 times 33 divided by 75 gives us a value of 12.32. 12.32. Now we go ahead and do that for the next one. And again, you may want to write this down yourself as you're following along here, because I'm going to have to erase in a moment, and we're not near the end of the problem yet, but I'll be out of room. So then we move on to this next one right here. Well, we take the total of, or the sum from the male row again, which was 33. Doesn't matter which order you do these in, multiplying goes in either order, commutative property. And then we take the total from that column, which was 47. We multiply those together, and again, divide by the grand total of 75. And this time we get 20.68. 20.68. Moving on. We now are going to look at this value right here. We take the total from its row and its column. This time we see 42 and 28 getting multiplied together, again divided by the grand total. And 42 times 28 divided by 75 gives us 15.68. And then, last but not least, we take our rows here. We've got 42 times 47, all divided by 75. And we get 26.32. So what did we just find? We just found our expected values. Now, the goal of this lesson is not to find expected values. The goal of this lesson is to find chi-squared. But for our chi-squared formula, the formula says chi-squared is equal to the sum of my observed data minus my expected data squared, all divided by my expected data. So in order to do chi-squared, I need what's called expected data. And what we just found, we found the four values of our expected value. I'll write it down here so that we've got it handy. It was 12.32, 20.68, 15.68, and 26.32. Those are the values we just figured out. Our observed data are the values we ignored from earlier, these four original values here. Well, order of operations. What's the first thing we need to do? We need to take our observed data and subtract our expected values. We see that right up here in this parentheses group. So I'm going to make a little table here. First thing I'm going to write down is my observed data. And for that, I'm just going to read my values. I had 12, 21, 16, and 26. So I'm just going to write those down. 12, 21, 16, and 26. Just reading it from left to right, top to bottom, just like I would a book. And now I'm going to put down my expected data, which we just figured out, which is 12.32, 20.68, 15.68, and 26.32. Now, what's the next thing? Well, we see I circled it up here. We are going to subtract those values. So I'm going to take my f of O minus f sub e and find those values. Well, 12 minus 12.32, these values right here, I'm just going to subtract them, so I end up with negative 0.32. Then 21 minus 20.68, I get positive 32. And then here I get positive 32 again. And then finally, negative 0.32. When you only have 4 pieces of data like this, you will see that sort of symmetrical pattern that we have there. But as we get more and more data, the pattern will go away. What's next? So we subtracted. The next thing I see in my formula is this squared sign. So we have to take all these values that we just did, f sub O minus f sub e, quantity squared. So whatever I just had, these negative 0.32s and the positive 0.32s, I am going to square them. And for each one of these, remember, a negative times a negative, use parentheses in your calculator if you need to type that in, becomes a positive. So really, all these values here need to be positive, and otherwise the numbers were the same that I had. 2 negatives become a positive, 2 positives become a positive. And so those are my values there. Now it looks like I'm just getting the same thing, but you will notice that in the next column I do not, because what is left? Left, I have to take all those values that I have now and then divide them by f of e, f sub e. So f sub O minus f sub e, quantity squared, which I already figured out, now divided by f sub e. So I'm going to take this value right here, this 0.1024, and I'm going to divide it by my f sub e column. So for the first one, it was 0.1024 divided by 12.32. And I'm getting a small little decimal of 0.00831. I'm going to round there. That's 4 significance. Now, why am I rounding to 4 rather than 3? It's not my final answer. So I want at least 1 extra. 2 or more would be even better. The next one, I take the same value, the 0.1024, and divide by my next f of e, which this time is 20.68. And I get 0.00495 2 approximately. And moving down the list, I take 0.1024 divided by 15.68, 0.06531, and then last but not least, that same numerator, this time divided by 26.32. And that gives me 0.00389. So now I'm going to, we're still not done. I've got sigma. What does sigma mean? It means add it up. So I'm going to add up all these things that I have. So these last 4 values I have here, I'm going to add them all up, which will take me just a moment. 0.06531. And I end up with approximately 0.0237. What is that I just found? It is chi-squared. Again, I rounded to 3 significant figures. 0.0237, chi-squared. Ladies and gentlemen, that is chi-squared by hand. Now, we have done other hand calculations on these videos, and I said you don't need to know them. You need to be able to do this. So next class, I will give you a worksheet that sort of walks you through this process, step by step, how we do this. And honestly, this isn't even the end, because then we need to be able to interpret that data. But that's another day. This is not as hard as it seems, but it's very new, and there's a lot of things going on. None of the math was hard. I mean, what's the hardest thing we did? Added, subtracted, squared, you know, like nothing too fancy going on here. And I can show you how to do this with technology on a later lesson as well. But for our projects, we're going to have to show how we can do this by hand. Our goal is to be able to do at least one sophisticated technique by hand, and this is the one that I recommend we do. We could do a project involving standard deviation or some of the other math that we've done, but I find that most students enjoy this one the most. So we will succeed, but you'll have to persevere, meaning that you practice, you follow along, and I have a couple problems that you can take a look at here. Skipping ahead. On page 337, number 2, 3a, and 3b, you might want to take a look at those, see if you can find some chi-squared values. Next class, we'll have a worksheet after our test on correlation, and we will see you next time.